Hello, good afternoon, everybody. Welcome to the GeoTalks. First of all, I would like to thank also John Hancock, that is our sponsor, and thank you to everybody that joined today to listen to Vikki's talk. I met Vikki in 2015 in Pilbara. I'm very excited to have her today here. And Vikki Hansen, they want my video, so I'm going to start it. Vikki Hansen is McKnight Presidential Professor of Earth and Planetary Science at the University of Minnesota, Duluth. She's a structural geologist interested in the dynamic evolution of planets. Her work focuses on Earth and Venus, but draws on insights from the Moon, Mars, Mercury, and Jupiter's and Saturn's moons. Vikki developed a hybrid approach to planetary science research, combining two seemingly different tracks. Firstly, there is field-based research on Earth, with fieldwork in Alaska, Antarctica, Arizona, Australia, California, Canada, and Minnesota. And secondly, she uses the remote sensing data from Venus. Most planetary geologists use Earth analogies to understand other planets. Vikki flips this around, using the geologic record read from Venus' intricate surface to discover the nature of Venus' tectonic processes. These discovered processes may in turn provide critical clues about Earth's Archean aeon. And I thank very much everybody for being here. Please welcome Vikki. Vikki, the stage is yours. Thank you for being here.
Thank you so much, Linda.
And
thank you all for coming today. I really appreciate this opportunity. And I want to just give a shout out to Wits. I'm so impressed with the whole talk series and how you're bringing people in from all over, but also to make these incredible talks available globally for people. It's just an incredible opportunity for the sciences. So I'm going to go ahead and share my screen and get started. So as Linda said, I'm an Earth trained geologist, but serendipitously went to Venus and felt that Venus had a lot to teach us about planet Earth. And so that's what I'm going to talk about today. I grew up with a couple of sisters and a brother, and for any of you who have siblings or know people who have, I think that siblings, by studying them, you can learn a lot about the family. And I think the same is true for Venus and the Earth, terrestrial sisters. And when we look at Venus, Venus never developed plate tectonics, so she preserves incredible spatial clues, especially for early on in the history. Earth developed plate tectonics, but we have geochemical clues that we can get from Earth that we can't get from Venus, not having been there. I like to really think of Venus as having the pages of the baby book, and we could use these baby book pictures for either planet early on in their history. If we take the clues from Venus and Earth together, I think that we can envision geodynamic processes that we otherwise would not be able to imagine. So I'm going to start with just giving us a little bit about Venus, because most of us don't study this planet. The data comes from the NASA Magellan mission, and there are basically four parts to it: radar or SAR imagery, very high resolution. That's the main data set we use, but also altimetry data, and that is lower resolution, but these are all global data sets. And so when we think about the altimetry at the global scale, it gives us a lot of information. We also have gravity data that allows us to see into the subsurface. It's non-unique interpretation, and the emissivity and reflectivity data that were collected with Magellan aren't used very much, simply because there are so many parameters that come into their interpretation. We haven't cracked the code on those. So the setting, the atmosphere on Venus is supercritical CO2. A couple of other things tossed in there. Surface conditions, it's hot and high pressure. The surface is proposed to be basalt, but it's ultra dry basalt, and Therefore, it has, despite the high geotherm, it has a slow lower crustal flow rate. The surface heat flux, you can see there, the lithosphere we basically take as similar to the Earth. The best analog for kind of garden variety lithosphere would be the Earth's oceanic lithosphere for Venus. And the mantle current temperature and viscosity, we take pretty much similar to the Earth's. I want to point out that there's no robust time constraints on Venus. And that's because when we go to terrestrial planets, or icy bodies, we use impact crater density. And Venus has 1,000 on the surface, but that's really not very many across a planet essentially the size of the Earth. So no robust absolute time constraints. Now, most approaches for studying Venus are twofold. Geophysicists consider the planet globally, but in little detail. Geologists consider the details, but really across small areas. Small is all relative to term. Some of the even largest maps are on the order of 7 million square kilometers. In this study, what we're going to do is to focus on detailed structural mapping across a very large scale. So the map area that we'll be looking at covers over 25% of the surface of Venus. So the outline for the talk is to give us just a global perspective, but then we're going to focus on this Niobe Aphrodite map area that covers 25% of the surface. And we're going to look at the structural mapping to understand some tectonic regimes. And what we're going to find are 3 tectonic regimes: an ancient era, Artemis superstructure era, and a fracture zone complex era. And we're going to focus on these 2 with lessons for the Earth. The fracture zone complex has some lessons on Earth, but we're not here for a couple of hours to go into that. So just to make an Earth and Venus comparison for the scale of the area that we're looking at. Here we've got 2 maps of the Earth that you probably recognize. Colored, each of these color blocks would be the size of the Niobe Aphrodite map area. So the purple or any of these. And the reason I put this up is to illustrate that when we look at this map area, no matter where it would be, we would be covering numerous plate boundaries if we were mapping this size area of the Earth. On this map, it highlights the Archean cratons. And again, either of these color blocks would represent the Niobe Aphrodite map area, and we would also capture numerous Archean cratons. So this is the data set that we'll be using, the radar data. It's a phenomenal data set. The Magellan mission was the first all digital mission. And we have 98% coverage, 100 meter per pixel resolution. We have no equivalent data set on Earth. And this is just mind-boggling, and we'll be mining this data for an incredible time to come. The altimetry data shown here on a static laid out view of the whole planet we've got is all reference to mean planetary radius. No water on Venus, no sea level. Venus is an incredibly circular planet or spherical planet, and so mean planetary radius is a good reference. When we look at this topography, the first thing we might notice on a hypsometric plot is that the hypsometry is unimodal. On Earth, we have bimodal topography, the ocean basins and the continents. On Venus, it's unimodal, so one peak. The highlands are shown in red, the mesoland regions in yellow, and the lowland regions in blue. Within the highland regions, we have 2 basic geomorphic types, and they're shown in red and blue. In red are volcanic rises, and those are, they're both 1 to 4 kilometers high and have a quasi-circular planform. The volcanic rises are supported by mantle plumes, and these are contemporary features because they're thermally supported. Crustal plateaus, on the other hand, are steep-sided, flat-topped. They're going to be something we're going to focus on in this talk. They have a low-density compositional root that is what's holding them up high, and these are ancient features. And then we have two unique features on the planet. There's only one of each of them. Ishtar Terra up here, which is a continent-like region, and Artemis, which has a very circular trough along there and a unique interior region. When we look at the planet's surface, as I said, there are about 1,000 impact craters on the surface, and you may have heard that Venus was catastrophically resurfaced. This was an earlier proposal that people have hung on to, of which there is no evidence that requires it, and an awful lot of very strong evidence that actually does not allow catastrophic resurfacing. One of those is when we look at the impact craters, one can recognize stages of crater degradation. And why that's important is that means we can differentiate old craters and young craters. And when we plot old craters and young craters relative to the crater density distribution, we can actually divide the surface into 3 average model surface ages. This would be like a samarium neodymium average model surface age of extraction of melt. And what this means is that Venus could not have been catastrophically resurfaced. If it was catastrophically resurfaced, we would have a singular average model surface age. We can see even more about that when we take those average model surface age provinces and just see what those look like relative to volcanic rises and crustal plateaus and to lithodemic map terrains that we'll look at today. Ribbon tessera we'll get into, and fracture zone terrain. And all I want you to take away from this is to say, wow, there's no coherent spatial correlation with these things at all. And you say, exactly right, which means that there's actually a rich history across the planet that is not encapsulated by these average model surface ages. And we're going to try to extract some of that history today. So let's go to the map area. So this is the map area going from 57 north to 57 south, the equator's in the center, and we're going from 60 degrees east to 180 degrees east, so a fair chunk of ground. This is altimetry data that we're looking at here, but now with a grayscale, and this will be the base for our mapping that we will look at. The high regions here are crustal plateaus, so ancient features. We're going to start with the oldest, either lithodemic units or structures, and move up in time. So the oldest is this tessera terrain or ribbon tessera terrain. These are radar images here, and this is a 3D radar image. If you blur your eyes a little bit, this should look, and lean back, this should look 3-dimensional. We'll look at these in more detail. We see that the ribbon tessera terrain characterizes the crustal plateaus, but we also see it in the lowland regions. Moving up in time, we see very fine scale lineaments. Here's a radar image of it. Notice the scale in each of these. And these come in 2 sets that are orthogonal to one another and distributed over incredible areas. We do not know how these formed, or if they even represent singular suites, coherent, genetically related suites. Within the tessera, there are ribbons and folds, which I show here, and we'll talk about those later, but we also have folds that are not in the tessera terrain, and those are in deformation belts. And here's a radar image of that. Again, notice the scale there. The deformation belts occur mostly in the northern part of the map area. So if we take a closer look at that northern part of the map area, again, note the scale. These are some of the structures that we see that are earliest formed structures across this region. Moving up in time, We look at structures that are illustrated here in the radar image, fractures, very straight linear features, and wrinkle ridges that look like clothing wrinkles. And wrinkle ridges are a structure that's been recognized on all of the terrestrial planets. But here they have an orthogonal relationship to one another. We mapped those out here across the map area. The wrinkle ridges, these structures are shown in the yellow, and the fractures are shown in white. And what you might be able to pick out here is that those wrinkle ridges form a concentric pattern around Artemis. This is the Artemis structure right here. And the fractures form a radial pattern around this. Those radial fractures, which are probably dikes at depth, have an overall diameter of 12,000 kilometer diameter and footprint, and the wrinkle ridges have a cover a 13,000 kilometer diameter footprint. Taking that away and moving up in time, we see other structures, steep scarps and chasma. Chasma are simply troughs. And we also have other radial and concentric structures, but these are at a much smaller scale than the Artemis related structures that we saw. Circular, you can see the radial patterns there and there and there, and some of them come with associated concentric structures, and in other places we have concentric structures with no radial patterns, or radial patterns with no concentric structures. But what I'd like you to note is that these are much more localized now, and forming, well, more localized pattern at the scale of the map area. Also within this fracture zone complex, we have extremely penetratively developed fractures highlighted here in the white lines, different than the radial fractures that we saw around Artemis. And we have pit chains, which are structures we see in Hawaii today. These are magmatic structures, subsurface structures where we're actually stoping magma to depth and carrying it away. All of these features that we see here in this fracture zone complex are tectonomagmatic features. And we can see that they form kind of, they aren't everywhere across the map area. They form in relatively discrete zones. If we take a little bit closer look at zooming in on the fracture zone complex here, we can see that it's narrower here, but still a wide region. Note the scale, but then it bifurcates into kind of arms going up like this and even off up that way. Notice that it cuts into the earlier formed crustal plateaus, and particularly with those pit chain structures shown here in the hot pink. So really quick, here is 8 to 10 years of detailed mapping by myself and my dear colleague Ivan Lopez in Madrid. And these are the structures across this map area. And the first reaction to this might be, yikes, that looks like an incredible mess. But it isn't a mess when we really start to characterize these structures, look at cross-cutting relationships, and see them in through time, as I tried to take you very quickly through before. And so here we've got all of the structures, but I'm going to simplify these into different tectonic domains. In purple are the ancient era, in red, covering the whole region, would be this Artemis superstructure, and in the light blue would be the fracture zone. So we can take those away, and now we can say, here's the simplified sort of tectonic domain map of Venus. This is probably an important point right here. I use tectonic, and a lot of people say, wait, I thought you said Venus doesn't have plate tectonics. Plate tectonics are only one type of tectonics. Tectonic simply means basically deformation of a planet's surface. So Venus certainly has tectonics. So we can look at these, and actually we're stepping through time with the development of these structures. And so now what I want to do is to say, well, what does that tell us about what was going on in those periods of time? What were the geodynamic processes? So we look at this ribbon tessera terrain, and this is a proxy for this ancient era, absolutely distinctive terrain. It covers 12% of the surface. It occurs in the crustal plateaus, but also you can see within the lowland regions. And it is present in some of the deepest basins. Again, if we had catastrophic resurfacing of the planet, it could not occur in these deep basins because those basins would have been catastrophically filled by lavas. When we look at the patterns of the tessera within the inlier, so we're in the lowlands here, now we're in these mean planetary radius. Again, we're in altimetry for our base. So we're in a low region. In the light blue here are the ribbon tessera outcrops, and the outcrops as well as the structures and the structures within them, and we'll see those in a moment. There are fold trends and something called ribbon trends. Both the outcrops and the structures themselves form actually patterns that we can map together from these isolated little inliers. And this tells us that they have some sort of shared coherent history, even within the lowland regions. So going back to this ribbon tessera, what I want to do now is just look at what that tessera looks like. We're going to take examples from Avda Regio, the biggest of the crustal plateaus there. And so this is what this ribbon tessera looks like. Now, this is a red-blue anaglyph image. So I didn't give you guys red-blue glasses, but if you blur your eyes and lean back a little bit from your computer, hopefully this will look three-dimensional. What you should see is parallel to these ribbon trends are ridges and troughs, ridges and troughs. If you take your fingers, your hands with your fingers, and you open your fingers up like this, you see ridge, trough, ridge, trough, ridge, trough, a periodic structure. And that's what the ribbon structures look like, sort of like a corduroy fabric. The ribbons are as long as 150 kilometers long. The ridges and troughs are only a couple of kilometers wide. So they have these incredible aspect ratio and periodic development across the crustal plateau. Extremely unique type of feature. Here in another red-blue anaglyph, we have the ribbon trend of this orientation, fold trend, again, perpendicular to it. Here, the folds are actually much smaller, shorter wavelength fold structures. Again, blur your eyes and lean back from that. What I want you to see is the ribbons and the folds are orthogonal to one another most of the time across all crustal plateaus and across all inliers. As we zoom out a bit from those structures, here we can see the ribbon structures of this orientation, northwest orientation. We see longer wavelength folds as well. Note the scale here. I've mapped out the axes of anticlines, synclines, and these are actually very, very gentle warps across the surface. If we zoom into this region here, we'll capture some of these folds, but we'll be able to see the smaller scale structures as well. Again, in a red-blue image, this is, note the scale here, so we've zoomed way in. And in the next, this whole surface actually looks a lot like the surface of a Pohoihoi lava flow, but at a completely different scale. Adding some annotations might help you to see some of the structure. These structures of this orientation, northwest trending, but closely spaced, would be ribbon structures. Similar orientation, but formed later, are graben complexes. They're very short and wide in comparison to the ribbon structures. The folds, all the folds, long, short, and intermediate wavelength folds have the same orientation, northeast trending. We also have regions that are radar dark right in here, shown very well, and that is flooding, volcanic flooding that's taken place in the the troughs of these features. Someone asked if the uniformity exists across the area. It is, these structures are not always, I hate to ever use always, but let's say 90 to 85% of the time. So something that needs to be addressed in the formation of these structures. If we zoom into, whoops, this is the area we zoomed into. I'm just going to zoom out a little bit now and look at some detailed mapping. So I've put the map over the radar image, so you can just sort of see how they're related. And now I'm going to take that radar image away or fade it so we can see the map. And the we have short wavelength folds, intermediate wavelength folds, and longer wavelength folds, all parallel to one another in this area, which is common across tessera terrain. And perpendicular to that are the ribbon structures, here shown in blue. I didn't map all of those. We would have covered the region if I did. And also some of the complex graben shown in the brown. Again, orthogonal to one another. And in purple is the flooding of regions. And the flooding takes place at structural lows from the shortest of scales up to these very large scale images. One more red-blue image to share here. And this is not representative, but it occurs over some very large areas, particularly in terms of obduregio. And this is extremely, extremely closely spaced ribbon structures and folds. And the folds look like rumpled up cloth. This really looks like a piece of rumpled up fine corduroy. And this is developed over an area that's greater than the entire Eastern Cape region of South Africa within obduregio. So trying to put all of these together, now this is the area that we looked at of a map area. Some complexity here I'm going to try to take you through. This is a stylized cartoon block diagram to try to capture what these structures look like in general for ribbon tessera terrain. So we have fold structures, short, intermediate, long wavelength folds, all parallel to one another. Perpendicular to that are extensional structures, these ribbon structures, think your fingers, and complex graben that are short, fat extensional structures. What's important about these periodic structures, both the folds and the ribbons, is we can use that periodicity to say something about the thickness of the layer that is being deformed. And so I've got layer thickness calculations here. These are the short wavelength folds, so this is in kilometers. The ribbon structures overlap that, and the medium wavelength folds overlap that. Why this is important is it's saying that we are actually forming these things, broadly speaking, at the same time. But the short wavelength structures are forming first, with the longer wavelength structures forming later. We can also look at the fold wavelengths. And as we go from short to long, the layer thickness, the layer that is being deformed gets thicker, the amount of shortening goes from very high amounts of shortening with the short wavelength folds to very low amounts of shortening to the long wavelength folds. It turns out when we look at these fold structures that in order to generate these types of fold structures, it requires an extremely high viscosity contrast between the layer that's being deformed and what is beneath it. Prior to this study, I had thought that that layer was just a ductile solid. It can't be a ductile solid. The viscosity contrast has to be so great that the layer and the subsurface the subsurface region must be a liquid beneath it. So as we go through time here to develop this in just a two-dimensional picture here, we have a thin solid layer above melt. That layer is shortened in this dimension, extended in the perpendicular dimension. The layer thickens, it continues to be shortened, and those earlier formed short wavelength structures are carried piggyback on longer wavelength folds, and then shortened some more and continued to carry piggyback, and so that we have this structure here reflected in the structures that we see in our block diagram. What this tells us is that the tessera terrain across a single crustal plateau, the largest of which is on the order of 2,400 kilometers across, formed as a scum on a huge pond of lava. All of that lava had to be there in place. We had convection in that pond that led to the development of this distinctive fabric. So then this raises a huge question. How on Venus could we have formed such a huge pond of lava? And in order to answer that question, we actually come back to Earth. And in 2004, Engel and Coffin proposed that the Ontong Java Plateau here on Earth was formed due to bolide impact on young, thin oceanic lithosphere. It doesn't actually matter whether that is a correct interpretation or not. We're not going to bog down into whether that would occur. I mean, whether that is how the Ontong Java formed, but modeling was done as a result of that. And the first modeling by Jones et al. And basically said that, yes, indeed, if we take 10 million year old lithosphere, there's our mantle potential temperature. In this says 10 minutes, it's actually in 20 seconds we can generate the melt that is required. It really tapers off, so you add 10 minutes, you add an hour, you even add a couple of years, you don't generate that much more melt. So and then other modeling since then has only shown that indeed a large bolide on thin lithosphere generates a lot of melt. So if you have thin lithosphere and if you have a large bolide, you get instantaneous melting. You get a huge volume of melt. Equally important, you get 50 to 65% of fractional melting. This is taking place in the ductile mantle. So that means that if you're generating this huge volume of melt, you also get a mantle melt residue. The higher the mantle potential temperature, the greater the melt. How much melt? So how much melt is actually generated? No one's done the modeling exactly for this, but we can take some of the models and answer that, and how much melt is needed. First, let's get to how much melt could be generated. A 30-kilometer bolide impacting a 50-kilometer lithosphere. I'm going to call your attention to on Venus. Early Venus probably didn't have a 50-kilometer thick lithosphere. It was probably closer to 10 kilometers, much less than 50. But this is what we have to work with. If we have different mantle potential temperatures, this was probably a best, if not the mantle potential temperature even higher, we're going to yield this much melt following the study here published in 2005. If we go to oops, I'm sorry, this should say if we go to 700, I think, then we're going to yield even more melt. Oh no, this is the conservative estimate, sorry. How much melt is needed? Well, we don't know that either. So ancient Venus lithosphere was probably 10 kilometers thick, could have been a little bit thicker. So a 1 kilometer deep lava pond would require this much melt. This is on the largest crustal plateau of Opteregio. If we have a 5 kilometer deep pond, this is how much melt is required. So just compare that. We have no problem developing that much melt. 10 kilometer deep lava pond, which we probably don't have, we still have no problem developing that much melt. So again, we can certainly do this. We'd like to have better modeling, but there's no problem even with the most conservative estimates. So let's go ahead and form a huge lava pond. Ancient Venus, we had a thin lithosphere. We have a large bolide. And what happens? The bolide punches right through that thin lithosphere and causes massive partial melting in the ductile mantle. It causes high fractional partial and high fractional partial melting, up to 65%, possibly more with a higher mantle potential temperature. So that melt is going to rise to the surface through fractures and form our huge pond of lava. That pond of lava is going to crystallize to form our ribbon tessera terrain, and we'll be able to get the entirety of the fabrics that we have. Down in the mantle, that mantle melt residuum that is left behind is extremely magnesium rich. It's very buoyant, it's dry, and it's strong. Once we form it, we're not going to easily recycle this stuff. If that mantle melt residuum remains in place, once that pond is crystallized, this mantle melt residuum, which is lower density than the mantle around it, is going to uplift that whole region and allow us to form our crustal plateau. If that mantle melt residuum is swept away, then that crystalline lava pond will not be risen up, and it'll just stay at the same level in the surface. In this case, younger melts that would form elsewhere, or flows, I should say, could variably cover it up, and we would have the tessera inliers that we see globally across Venus. If that residuum stays in place, as the planet secularly cools, we're going to thicken the lithosphere and lock that residuum in place so it can't be lost once we have thickened that lithosphere. And in that case, when we have younger lava flows forming at the surface, they won't come up and cover the crustal plateau as we see, but they'll just lap up against the edges. So to put that all back together in a kind of cartoon format, we can form our lava pond up here and our mantle melt residuum. And if the residuum is swept away, we have a tessera inlier. If the residuum stays in place and is then locked in place, we have a crustal plateau. So this allows us to both address the crustal plateaus and the tessera inliers that we see in the lowland regions. But this gets one to thinking, saying, okay, these are unique features on Venus. They only formed at this ancient time period. And Earth has some unique ancient features, and those are called our cratons. And these are actually similar in size and shape, and maybe even in some regional structures. And when we think about it, Archean Earth, by many reports, had a stagnant lid, a thin lithosphere, and certainly had large bolides. So I'm going to propose that these crustal plateaus are actually analogs for Earth's Archean cratons. So the granite greenstone terrains and the subcontinental mantle lithosphere. So let's make a comparison briefly of these two. We're back to Venus. Oops, I should have said, here we are, we're going to jump into Thetis Regio right there, another crustal plateau. And I've chosen this because if I take this part of the superior province here, it's similar in size to Thetis Regio. I have sized these so that they're both using the same scale. Superior province up here in northern Minnesota, and coming to you from Duluth right there, whoops, right there on the Great Lake. What both of these have in common are crests of warps or broad, gentle anticlines. And I've mapped those in Thetis and in the superior province. And remember, these are shown at the same scale. So these features are at a similar scale. If we zoom in on the Abitibi province part of the superior province, snatching a map from Phil Thurston shown here, I've mapped out the crests of folds at this scale, or really broad warps here. And these are all upward facing based on Phil Thurston's work. And going back to Venus, this image here is also at the same scale as the Abitibi map that I just showed you. This is the region we looked at before, and these are the crests of anticlines and synclines here on Venus. So again, a similar scale. Jumping over to some other tessera terrain, We have gorgeous features here. Some of you who work in shear zones might recognize that we have, that these look like SC type fabrics. And indeed, I think that's exactly what they are. So we have these ductile shear zones that are forming relatively late during the evolution of these tessera terrain. And if we jump then to Australia and the Pilbara craton, we also have large-scale crustal shear zones that have been mapped in that region there as well. The Archean cratons not only have the upper part of them, the granite greenstone terrain and komatiites, but of course they have this important root. And that root is also distinctive. It's extremely high magnesium, more so than younger subcontinental mantle lithosphere roots. It's extremely buoyant, strong, and dry. And I hesitate to put this on given where I'm talking about, but the diamonds are unique within these roots as well. So again, I suggest that we're forming these cratons by an exogenic process, or that was a key driver in the formation of these. Well, let's go to that period of time and say, if I want to form it exogenically, I need some evidence of large impact events. And we definitely have evidence of large impact events. We have spherical layers in the Barberton greenstone preserved. Not that that is an impact event there, but that's spewing the results of impact events. And if we look at modeling of the late heavy bombardment on this plot here, we have billions of years along this scale and along that axis, and total impacts. And these are for bolides greater than 25 kilometers in diameter. The conventional late heavy bombardment is actually mapped for the moon. But Earth was affected as well. And in fact, Earth was more affected than the moon, because if it hit the moon was not protecting the Earth. The moon isn't sitting there catching things. The Earth caught a lot more. So here we have the curve for the Earth, and I have just put on here the time period for the Archean, and notice that we're losing those large bolides by the end of the Archean. We have plenty of them during that period of time. So remember that if we have large bolides hitting thin lithosphere, we are going to get massive amounts of partial melt. Archean Earth had a hot mantle, a thin lithosphere, and was pummeled by large bolides. So I think we have to ask the question, what did happen at that time when the Archean Earth thin global lithosphere was struck by large bolides? So there we have our thin lithosphere. There we have our bolide. It goes right through that thin lithosphere, causes massive partial melting. That melt rises, doesn't form tessera terrain in here, but I'm going to say a huge igneous province. Maybe we could call it a hip as opposed to a large igneous province. These are much, much, much bigger than the large igneous provinces we have of younger age. And we have mantle melt residuum forming in the mantle. The crystallization of the mantle of the melt pond here could be quite different than Venus, because it would all depend on the atmosphere and the rate of cooling. I can go into more details with regard to questions, but I won't. I'll just leave it at that now. The other thing is remember that in granite greenstone terrains, we're looking at eroded down deep into these features, whereas on Venus, we're actually looking at the surface features as they formed and were preserved from that initial time period. Within the mantle, we have the mantle melt residuum is the subcontinental mantle lithosphere, which would be extremely high magnesium, buoyant, strong, dry. Once we form it, we're not recycling this. And we could also have those Archean diamonds forming there. So when we look at all of the cartoons together, now in the case of the Archean, we can form this in the same way that we would do with Venus. But if we lock that residuum in place, we have an Archean craton. If that residuum is moved away from the huge igneous province at the surface, then it just becomes part of that crust. And this would probably be recycled to the mantle once the planet forms plate tectonics. So back to Venus again. Venus, remember, has these two unique large features. It has the Artemis superstructure here and Ishtar Terra. The superstructure is circular in footprint, which means it's punched from above or below. It cannot be punched from above. An impact would not form a structure that looks like this. So the bigger it is, the deeper it is. This is an endogenic structure, not an exogenic structure. We can see just how big it is on these two global perspective views. There's Artemis Chasma right here. Artemis Chasma for reference there and there. In this case, the red represents the wrinkle ridges and the yellows represent fractures. Ishtar Terra, the other unique feature on the planet, is this region up here, and it's a continental-like region. And back in 1995, Roger Phillips and myself, through structural and gravity study, determined that this area is held up by a huge, deep crustal root of mantle melt residuum. Like our big continents today, we did not know where that mantle residuum came from or how it got there, except that it was collected in a downwelling. I think we know both of those things now. I think these two are actually related. They're near antipodal from one another, and I don't think that is a serendipity. To try to understand this, let's go inside the planet here. So we've taken Google Earth and made it into Google Venus. Here's the core, the lithosphere. I've tried to draw things pretty much to scale here. The Artemis superplume would have formed at the core mantle boundary. That Artemis superplume would rise up, hit that lithosphere, and then start moving out. When it rose up and hit that lithosphere, we'd form all of those huge radial fracture sweep. It's going to sweep around until it ultimately cools down and then goes into a downwelling. When it sweeps around, it's going to sweep out any thing that is mobile in that ductal mantle, and that could be earlier formed mantle melt residuum that is able to be moved. As this plume, and all of that mantle melt residuum would collect where this global downwelling went down, and that would be, in this case, Ishtar Terra. I think that's how we got all of that earlier formed mantle melt residuum into this deep root of Ishtar Terra. Again, unique on the planet. The Artemis superplume, when it decayed, the surface would collapse, and that's when we would form all of those wrinkle ridges, kind of like a deflated balloon. The Artemis superplume decayed and just went into the form of the Artemis plume as the last gas, and that's when we formed that Artemis Chasma that we saw later. That's that we saw earlier, a story for another time. So when we think about Venus and Earth now in these early years, and thinking then about geochemical implications, I think Venus gives us incredible spatial implications. On these two panels, what I'm trying to focus on here are the rock reservoirs. So as we start in the Archean eon and the ancient era on Venus, we have an atmosphere on Earth, maybe an atmosphere and an hydrosphere. We have lithosphere and mantle on both planets. Those are the two simplified rock reservoirs. Put in a large bolide. We can do this several times, but we'll just focus on doing it once here. This region right here that's affected by that bolide is going to form two components. A part that I'm calling C for crust, and a part that I'm calling R for residuum. The crustal melt goes up and is going to form on the lithosphere and either form a tessera terrain or granite greenstone terrain. The residuum remains in the mantle. What becomes important of these two rock reservoirs is they are no longer in chemical communication with one another. If those two stay attached to one another, but not in chemical communication, we'd have a crustal plateau on Venus and we'd have a craton on Earth. If they become detached on Venus, we have a tessera inlier, and that inlier is preserved because we don't have plate tectonics. On Earth, that would just remain as Archean crust if that residuum is decoupled from, moved from beneath. On both planets, we could have residuum that is formed in this way, actually swept around in our ductal mantle and form a continent in the case of Venus, Ishtar Terra, but we're forming this continent without any plate tectonics. I've heard from several people we need plate tectonics to form continents. I do not believe that we do. We could have done the same thing on early Earth. I think this has some really important implications for the petrologic evolution of the granite greenstone terrains, for geochemical evolution of crust and mantle in this early period of time. And I do not profess to be either a petrologist or a geochemist, so I'll leave those implications and tests of that to others. Moving on in time, as I said, on Venus, the tessera inliers would be preserved and are preserved. They're locally covered up, but we can map through and at least see their remnants. On Earth, if we have the Archean crust that's been decoupled from its residuum, it's now missing its life preserver, and this could certainly be recycled to the mantle once plate tectonics forms. And I expect that, in fact, it would be recycled to the mantle. So what I think that this would actually allow us are some of the apparent paradoxes that occur within the Archean Earth, and that is the paradox of undepleted mantle during the Archean, and yet evidence for growth of a significant crust. Notice that as I remove this material right here from the mantle, because I'm taking that part of the mantle, taking and dividing it into two reservoirs. Oops, I should move down here to Earth, dividing it into those two reservoirs, but then these reservoirs are separate reservoirs from the mantle. This would not result in depleting the mantle by this mechanism. So we could actually generate crust and residuum without depleting the mantle. So to just wrap up, the Archean on Earth has several unique features, but perhaps they're not actually totally unique if we expand our playground to Earth's sister planet, Venus. It may well be that both the Archean era on Earth and the ancient era on Venus represent very similar timeframes, and what large terrestrial planets would do. They would have thin lithosphere, there would be large bolides, and that this is a process that they kind of can't, that would occur on planets Earth-sized, Venus-sized bodies. So these pages of the early pages of their baby books are the same. If you look at my baby pictures, I'm the third of three daughters, boom, 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 and then younger ones. There are lots of pictures of the younger and older, but not very many of me. That's what happens when you're a third child, and also a girl when the others were girls. But I could use the baby pictures from my two older siblings and change them interchangeably. As we get older, we certainly change, but early on, very, very similar. And I think the same is true for Venus and Earth. So after this period, they went and evolved separately. Earth developed plate tectonics. Venus developed more of a vertical tectonics. And because of that, it's because of Earth's development of plate tectonic that it destroyed that early spatial record. It's because Venus didn't destroy that early record. She didn't rip up pages of both of their baby books. So with that, I thank you very much for your attention, and I would be very happy to answer any questions. Thank you.
Thank you very much, Vikki. Thank you for bringing us for some times to our sister planet outside of here. Yes, we all welcome questions. And I remind the audience that there are two ways to pose question now. They can just put it in the question answer, or if they raise their hand, I can also put them as a speaker. So if anyone has anything interesting or any curiosity to ask, actually Vikki is welcoming. And there is some compliments from Sue. Sue, would you like to say something to the panelists? There is a question here in the question answer. I have to. How deep a pond would this be? Or do you? There is this question answer. Maybe it was from early on. They ask how deep the pond were. Maybe
it's a really excellent question, and I have a simple answer, but then I'll go into. First of all, we don't know. But talking to Tracy Gregg, who is the one who did actually modeling work on surface flows of Venus and did the work that I'm drawing on that illustrates that with the structures that we're forming is what we requires that we have a strong deformable layer, but liquid below. And talking to Tracy about this with her insights from modeling, that her answer to that is that 5 kilometers would be plenty depth, but we don't know how deep it would be, or how deep it needs to be, or if there is a singular depth within there. And I think that's a really important question, but unanswerable, simply because when we think about, that's also tied to what the volume of lava is that we have. There's no problem generating the amount of lava with the models that exist, even though these models could be more sophisticated. First order models say there's no problem getting to, even if we have a 10-kilometer deep pond. But that would become very interesting from petrologic modeling in terms of the crystallization and the like. And that also brings into how would this crystallization, and would there be overturn in the pond? There might be more overturned if it was a deeper pond or less. And the atmosphere actually comes into play here. Venus's atmosphere is supercritical fluid, CO2. And what that means is that it changes the way that magma cools at the surface. And I can't keep up with all the proposals of Archean Earth, and it might change through the Archean, but how quickly we crystallize that pond would also come into play for petrologic constraints. So in short answer, how deep it is, we don't know, but from Tracy Gregg, 5 kilometers deep would be plenty deep to get the structures that we see.
Thank you, Vikki. Here there is a question from Sue. Says, would you expect any classic evidence of the impact process to be preserved from the ancient impacts on Earth?
Another excellent question. So thinking about this, probably no. And the reason for that is that these bolides would go right through the lithosphere like a BB or a bullet through glass. And so it's actually going to make a pretty small hole. Even if a 30-kilometer bolide on continental crust would make a 300-kilometer hole in the ground. Even if we had a 300-kilometer hole in the lithosphere, which we wouldn't have, that would be completely covered up by the pond that we see. Now, it could be you might say, well, would you have shocked features or things like that, shocked quartz? Probably not, because that's going to be what the target is. If that target lithosphere is probably a more basaltic or mafic lithosphere, we probably wouldn't have shocked quartz. And again, if we did, that would be all covered up. And so we probably wouldn't have what we think of as the kind of classical, what we would expect for a large bolide impact. If we look at the Sudburys or the vertiports that are significantly younger, and this is when we have a thicker lithosphere on the crust, and then we make a big hole in the ground, that's when we're going to start to see those features that we would identify with the large bolide impact.
Okay, Vikki. And there is a curiosity, have you found evidence of water on Venus in the study?
In this study, I have not. I know that there was recently published work in Nature on tessera, that it forms with water. And I would politely say that it is total BS. It ignores the data that we see here. It ignores the high resolution imagery. It ignores the periodicity of structures. Don't get me started. So no, I see no evidence for water in the features that we have seen within this study.
Yeah, Vikki, I have a curiosity myself, because in the Archean we see a lot of vertical structure. And I was fascinated by this picture that you have ripples, and then you call it like a scum over the pond, the melt pond. And okay, if something like this happened on Earth, I can imagine there is shortening because there is plate tectonic, the continents were moving. But what could that cause these ripples on Venus? Maybe
yeah. In this structure, these structures here. Yeah, that's a really excellent question. So these fine scale folds, short wavelength folds, go all the way down to our radar resolution, which at effective resolution for seeing folds is on the order of, say, a few hundred kilometers wavelength apart. And so how these folds are forming is they have incredible amounts of shortening. I should have looked this up because we calculated this. And if we just shorten this whole crust, that amount, our crustal plateaus would be 40 kilometers high. So that's very silly. It can't have happened. That also indicates that we did this shortening here, not shorten once we have this all this thick crust. The way that these folds are actually forming is due to convection in that lava pond. And so as the lava pond convects, and that could be another limit, back to that question of how deep does that pond have to be in order to convect, again, different limits, but 5 kilometers would allow that to convect. And if we have convection cells, we shorten that surface. We can see this if you go to Hawaii and watch a lava lake, in that case, that you get short wavelength folds forming, or even if you look at Pahoehoe lava flow, and I realize that's going down a flow crust, but you just can have flow underneath it that is shortening that. And that's how we also shorten it in this direction, but that crust actually extends in a perpendicular direction at that same time. Now, in terms of saying this is what's occurring on the Archean, it might be that we're preserving features of this, but for the most part, on the Archean Earth, we'd be eroding down into this. And so we wouldn't probably be preserving the surface. On Venus, we are preserving that formational surface. We're not able to see down beneath here in terms of that crystallization and what is going on. And so that's really important difference between those two planets in terms of what would be preserved.
Yeah, Vikki, I have other 2 questions here. Are you still holding for them? Are you?
Absolutely. We're talking Venus and Earth. I'm here, you know.
We have,
no problem.
It's very important to have questions for students, and here Marilee is our hero tonight. And he says, if Venus is very similar to Earth, why didn't plate tectonics develop there?
Yeah, I think that is another story. So you and I can talk separately about this. The talk was getting too long, so I actually cut this off. But it could first be that it might be more the question, why did Earth develop it and others didn't? Because Earth is the only body in the solar system that has plate tectonics. So Earth is the weirdo, not Venus, first off. But basically, once you start thickening that lithosphere, I think when we talk about plate tectonics, we need to develop two things together in time. A lot of the studies just focus on subduction, but we need to both have spreading and subduction forming at the same time. And another part of Venus, actually the Artemis plume, I think gives us hints about how plate tectonics, subduction and spreading, might have started on Earth. And they could have started at different places and then actually frozen up and not actually develop into the global geodynamic framework that we have today. So I can't go into the long answer. That's another talk. But again, Marilee, you and I can talk about this offline.
The last question is from Glenn. If the same mechanism of plateau formation is for Earth, is relatable to Earth Archean processes for Archean for craton formation, what is the implication on recycling the continent blocks, given that there is no record of plate tectonics?
Okay, so on Venus, we form those lava ponds, but they are not recycled and they are actually still preserved. So here on Venus, if I'm understanding the question, this panel is the same for both planets. On Venus, if that mantle melt residuum is removed, which I think it is, then the tessera, the crystallized lava pond sits at basically not at an elevated level, at mean planetary radius. And younger lava flows can variably cover it up. So we see little bits and pieces of it. So if we jump back to our global view here, we see the tessera preserved within each of the crustal plateaus that are circled in white here. These are regions that kept their mantle melt residuum root. All of these other regions of tessera, which are highlighted in this brown color here, formed lava ponds, but their roots have been translated, and we can just see the tessera in little bits and pieces that are preserved. We've done studies where if we look at this region, actually, we can figure out how the tessera almost certainly underlies this whole region within this circular region there. And we can do that globally across the planet to say that on Venus, that lava pond material just gets shallowly buried. It isn't actually recycled to the mantle.
Okay, we have you wanting to, you have to unmute yourself. Now you can talk.
Okay, can you hear me?
Yeah, we
Yes.
can.
Okay, so that very good, very great talk. Vikki, a new hypothesis that takes us between planets on an interplanetary scale, and some ideas that I never thought about. But I think you've got a pretty good story there. Now, my job as a scientist is to try to poke holes in it. Not that I wouldn't necessarily want to do that for any personal reason or anything like that. But you're going to have to listen to some people who are not going to agree with this.
Believe me, I have, and I welcome it.
Yes, I'm sure you have. One thing that I'm thinking of is that, if you make an analogy between the granite greenstone craton things on the Earth and these, what do you call them, tesserae on Venus?
Yeah, or crustal
right?
plateaus. Yep, depending on what you're.
Okay,
yep.
crustal plateaus. Well, you've got to in the greenstone belts, you've got to account for the fact that most of it is granitoids that are younger than the analogous things to your big lava lakes basalts and komatiites and stuff like that. That's only a very small part of it. And most of the cratons are granitoid, which I don't think you see any evidence for on Venus, at least in these plateaus. So you can respond to that. I have another question for you.
Okay, so first to respond to that, you're absolutely right. And I absolutely welcome questions all the time. I think the only way we move forward on science is to put out new ideas out there and listen to one another rather than keep finding information for the sort of same ideas. Actually, I will also say that the idea of forming the cratons by large bolide impact was, I won't get this right now because didn't look it up recently, but that was first proposed in the mid to late 1960s by Green, I believe. So it's a recycled idea. But to your question, on Venus, we're seeing the surface of these ponds. And so when we think about, crystallization and how these lava ponds with this kind of magma, I don't think we know how they would crystallize and how they would develop. So we've got to start to think about we being really petrologists in detail, not say, no, that won't work. That's not a way to actually move forward, but to say, okay, let's start thinking, if you just theoretically had a big pool of melt derived from the mantle that could or could not, you could run the models both ways, be contaminated by some felsic component, and that will depend on what assumptions you want to make. How is it that you are going to crystallize and evolve that body through time? And it is going to evolve through time, and the felsic material will only form at the, will stay magmatic or crystalline, will stay liquid for the longest period of time. It's those higher temperature materials that would crystallize sooner. And so we could well expect them to be younger, and it could be significantly younger, all developed depending on how this thing crystallizes. Is there overturn within this? And I'm not going to pretend to know the answers, but I'm also going to throw it back at petrologists and say, I'm also not going to pretend to say skepticism is okay without actually addressing that question of what would happen if we do that. So you might not be satisfied by that answer, but I think that it's really important that we ask questions of one another, but we also consider and then say, okay, I'll do that thought experiment as a petrologist, as a geochemist, and try to test these things and say, what would happen? Not, no, that can't happen.
Okay, thanks. I'll take your answer.
I think now we could have an informal conversation in a kind of a backstage. And I thank you very much all. So if you want to have to be part of an informal conversation, please raise your hand and I will put you allow you to speak. In the meanwhile, I thank everybody for the audience to be here. And I remind everybody that the GeoTalk is every Thursday. And next week, we are still in early Earth. And we are going to listen to a talk about Nadia Drabon from Harvard University. And she's going to speak about a new lens into the Archean Eon, about zircon from the green sandstone bed of South Africa. We also look forward to that. And I thank Vikki. I thank everybody for your participation and see you in the backstage.